Hi, I would like to introduce our work, CLIO, enabling automatic compilation of deep learning pipelines across IoT and cloud. Emerging advances in low-power sensor devices equipped with richer sensors such as cameras and microphones present significant computational challenges for machine learning at the edge. This is partly due to the volume of the data that needs to be processed and partly due to the complexity of deep learning models needed for processing richer modalities like images, audios, and videos. While an alternative to local processing may be transmit raw data or pre-processed data to the cloud for further inference, the main challenge is dealing with limited and variable wireless bandwidth. Bandwidth on low-power radios can be limited and change rapidly, so we need to find ways to be able to gracefully deal with bandwidth changes without compromising inference performance. We bridge the gap by an automatic compilation framework that leverages both local and remote resources to optimize execution of deep learning models while fitting to network dynamics. Our insight is that there are two complementary methods for machine learning under resources constraints. When bandwidth is limited, data compression is used to transmit reduced data to the cloud for processing, and when computation is limited, model compression is used to reduce the model size to fit into available resources. What we do in CLIO is to simultaneously leverage both model compression and data compression so that we can find the optimal way to take a large deep learning model and partition it to deal with resources constraints and variables in bandwidth. We use a layered deep learning model as an example to introduce our design. CLIO splits a deep learning model so that IoT devices will execute the early layers and local compute and network bandwidth will be utilized efficiently. But partition alone does not solve the problem of dealing with variable bandwidth. Unpredictable network dynamic is a challenge, as we either suffer from large latency than expected or tolerate much worse performance. CLIO enables intermediate features to be progressive so that when the network fluctuates and the cloud only receives limited partial data, the performance can degrade gracefully. Here is an example on the right. CLIO enables the model to learn ordered feature map, which we call progressive slicing, so that the feature maps can be transmitted in a progressive manner. Why do the ordered feature maps make sense for the network dynamics? For example, for each slice of the feature map, we have a corresponding head deployed on the cloud. When we transmit the intermediate feature map slice by slice and only one slice is received due to network dynamics, the specific model split will be used for further inference. Then the inference latency remains unchanged, while the performance of the partial data will also be good enough. We extend the benefits of progressively slicing by adaptive partitioning. For different network conditions, the best partition points of the model may be different, and adaptive partitioning allows us to adapt the partition points, so we adapt to long-term wireless variations. During training time, we learn the bandwidth operating regime for each partition point, and during the runtime, we use recent average bandwidth to determine what is the best partition points and slice to choose. We compare our methods, which progressively transmit slices, against progressive JPEG, which progressively transmit the raw data. For the same latency, we find out that our method can achieve better accuracy compared with progressive JPEG. Also, when the network dynamic occurs, our method can also degrade more gracefully than progressive JPEG. In summary, CLIO is an automatic compilation method for low-power IoT devices that progressively partition a deep learning model between an IoT devices and the cloud to optimize the latency and energy, while also be resilient to bandwidth dynamics. CLIO is a departure from our prior work, as CLIO operates in a progressive manner and simultaneously reason about the model compression and data compression. We have a complete implementation of CLIO on the GAP8 low-power neural accelerators and have also made the code available. Thank you.